Hi, everybody. Welcome to your first digital learning session with me, your favorite teacher, obviously, Miss Kylie. So today I'm going to go over some of the answers, not all of them, because I don't think you guys need me to necessarily go over every answer, but there are some that I want to point out from your first assignment, which was this paper. It says here paper 1 and 2, but really it was just paper 2 assignment for now. At the end of this, you'll also see that you have a new assignment that's going to be due on Friday. It's more questions on topic 4. I'm going to try my best to leave you with nothing to do over spring break, but get ready for topic 5 when we come back from spring break. Come back virtually, that is. All right, so looking here at 1A, I figured it was quite easy for you to deduce the electron configuration of bromine, but I just wanted to make sure on this note that you make a note of it, that bromine is indeed Br, and it's one of your diatomic molecules normally, right? So it is usually bromine, the liquid, which is Br2, just like fluorine and iodine and oxygen and nitrogen, all of those that come from our mnemonic, I have no bright or clear future, or I have no bright or clever friends, whichever one suits you best, maybe both of them. Br is the atom in this case though, so you should have done the configuration for just Br, and they gave you both answers here. This mark scheme is also going to be uploaded for you to view and be able to check your answers after I input your grade. Down here, they asked you to sketch the orbital diagram only of the valence electrons. So they only cared about the last level of bromine. That means that you had to consider the s and p orbital of 4s and 4p. Now notice that the energy line is pointing up. That means higher energy is up here. That is why they've placed 4s down here and 4p above it. It doesn't matter, you didn't have to necessarily have 4s here in the middle. I would have answered this like this, for instance. Here's 4s with the 2 electrons, and I would have just put 4p above. And this would have been totally fine. They tend to always put it, I know, I'm sorry, my writing is terrible. They tend to always put it inside of squares. That's fine if you had left it like this or done it like this. Either way is correct. The Lewis dot structure of this bromate ion, which is given to you, the formula, this is a negative, I hope you saw that, is going to look either like a single bond with 2 coordinate bonds, or 3 coordinate bonds. Notice they didn't even make them arrows here because that's not necessary. You could have written them as arrows or not. And the difference is dependent on whether you placed the electron on the bromine or if you placed the electron onto one of the oxygens. Like here, if you made a single bond, then you would have added your extra electron here and then done just coordinate bonds with the other 2. And if you added the electron to the actual bromine atom, then you would have done 3 coordinate bonds, because then you would have had all the lone pairs necessary to do so. The brackets and the charge are always necessary in a polyatomic ion, so make sure that you make a note of that as well. I'm sure that these were easy for you. I just wanted to point out that here when they say reason, especially given that I see it's only 3 marks, I figure I just have to give this answer, and then a quick answer here. All they're looking for is, why is this going to be pyramidal? Well, it's pyramidal because even though it has 4 domains, those 4 domains are made up of 3 bonding sites and just 1 lone pair. So that's all they're looking for. You didn't have to go into any other depth there. Here, for explaining the decrease in atomic radius from sodium to chlorine, again, I want you to start getting really used to looking at marks. 2 marks. I have to say 2 different things. I can say the nuclear charge or the number of protons increases across a period, while the same number of energy levels remains. So those are 2 different things you could have said. You could have said the nuclear charge is more effective across a period, but again, you want to not leave them with questions. So what does effective mean? It means there's more and more protons that are able to more and more strongly pull in on their outer electrons, because we can even compare them given they have the same number of electron levels. So anytime IB asks you to compare something, like here they want you to compare everything from sodium to chlorine, you usually want to make sure that you compare and contrast, right? So what is similar about sodium to chlorine is they all have the same amount of energy levels. To someone who doesn't know a lot of chemistry, that might mean that they're all the same size. But you know that despite having the same amount of energy levels, you also have one more proton successively as you go from Na to chlorine, meaning that the nucleus gets stronger and more effective at actually being able to attract in its electrons. Therefore, we move on to 2B. Explain why the radius of the sodium ion is smaller than the radius of the oxide ion. What I want to point out here is, again, it's worth 2 marks. Explain why the radius of the sodium ion is smaller than the radius of oxide. Again, you have to say something about both of them in order to get your point across. Here they use the word isoelectronic, whatever, I don't know, we never use that. Therefore, what I'm going to say is this instead. Let's say you had no idea what you were doing. I'm going to look at what Na plus and O2 minus look like. Na starts off as an atom that has 3 rings. Don't make fun of my circles. But when Na plus, right, loses that electron, it loses this outer level, and it ends up with 11 protons and 10 electrons. O2 minus always has 2 energy levels, and the only difference is it gains 2 electrons from the outside. So oxygen, which is number 8, starts off as 8 protons and 8 electrons, but because it gains 2, it has 10 electrons. That means what I can say about these 2 that they have in common is they both have the same electron configuration. They both have 10 electrons. They both have 2 energy levels. That means they both have the same electron configuration, which to someone, again, who doesn't know a lot of chemistry might think, well, then they must be the same size. But no, you know better, of course, because there's 11 protons in this one, whereas there's only 8 over here. Therefore, what I can say is they both have the same amount of electrons. However, sodium has 11 protons, or has more protons than than oxygen. Or you can say oxygen has less protons than sodium. Therefore, sodium shrinks inwards, right? The attraction is closer inward towards the nucleus, whereas for oxygen, the shielding is more at play, and you have a larger ion with oxygen. So why the radius of sodium is smaller? Because sodium has more protons, while oxygen has less protons, and yet they both have the same amount of electrons. For 2C, I'm pretty sure you're fine. Please let me know if you're not. 3A, I'm also sure you're fine, but I do get surprised at how many students forget how to calculate a percentage. So since they want how much nitrogen in grams is part of urea, right? Then all you have to do is know urea, and it's given to you here. Add all of the relative atomic masses of each atom together first, and that equates to 60.07 grams per mole. And then just take a division of the total amount of nitrogen over that whole. And so that should give you 46.65%. They did also say here, urea excreted by mammals, it's in our urine, is also used partially as fertilizer. Do you know what part of the urea is most important for fertilizer? Nitrogen. So that leads us to our next question, which I hate this question, but the reason I included it is they always throw in questions that have some sort of think outside the box notion, okay? That wasn't necessarily part of your curriculum. So here it says, I'm sorry, Mr. Darmus is speaking in the background. Are you done? He's done now. Suggest how the percentage of nitrogen affects the cost of transport of fertilizers, giving a reason. What? What do they want from us? I guess I would figure, okay, in the last problem, I realized that nitrogen only is 46% of the urea that might be used as fertilizer. That means it's not even half. It's not 50%. It's not even half of it. I'm guessing that to transport it costs a lot. So I'm going to say something like the cost increases and yet the product contains not even like 50%. And it doesn't even contain half of the nitrogen. Because I'm not sure what they're getting at. It's not in my curriculum. I'm going to do my best. And so these are the options they gave you. They're similar to what I said. Just go with what you can. You guys do really well at BSing. It's like been most of your high school career. In this question, I believe we actually touched on this in class. Just note that when you have multiple central atoms, they can just ask you to look at one. So here you can look at this nitrogen or at this one. They're going to be behaving the same. And so for nitrogen, you're going to say, okay, normally nitrogen actually has 5 valence electrons. And so in this picture, they just didn't include that there's a lone pair there. That means that nitrogen is surrounded by 3 bonds and 1 lone pair, making its electron domain shape tetrahedral and its molecular geometry pyramidal. The carbon atom is correctly drawn because carbon doesn't have lone pairs on it, and so there's 3 bonds and 0 lone pairs, which makes its electron domain shape trigonal planar, planar triangular. It's the same name. Don't worry how you state it. This one, I'm again not too worried, but here, in case, this would be the volume, while this here would be the concentration of potassium cyanate, which they pointed out is this molecule right here. So the potassium, formula unit. So this compound, you know its volume and its concentration, and yet what they want you to solve for is not that compound. They want you to solve for the mass of urea. And urea is over here. We know that because the beginning of this question in 3A gave us the formula. So you can always go back if you don't recall what something is. Here's urea. So what do you always need when you're going from one reactant to another substance in the equation, whether it's a product or another reactant? In this case, it's a product. You always need mole ratio. So you're going to solve for C equals N over V. That looks terrible. There we go. And so C is going to be the 0.100, and V, remember, is always in decimeters cubed. So that means you're not dividing by 50, you're dividing by 0.0500. That's just me maintaining the significant figures, okay? So to solve for N, you're going to multiply C and V. They do that here. And then you're in moles. You do mole ratio, which is obviously 1 to 1. So that's easy. That means that this is also the amount of moles of urea. And now that you know the moles of urea, you multiply it by its molar mass. And that is how you get 0.300 grams of urea. (3F) is actually in the slideshow topic topic 4, part 6. At the end of the slideshow, I actually gave a picture of the urea molecule to help you and explain that urea in comparison to ammonia. Ammonia is one of the ones you do have to know by memory. Ammonia is NH3. Ammonia is very small. If I build ammonia, I realize it has hydrogen bonds. But so does urea. Urea also has hydrogen bonds. We could see urea over here somewhere. Oop, not that far. Oh, maybe not. I don't have it here. Urea, though, if you build it, you'll notice is a huge molecule. It is polar just like NH3 is and also has hydrogen bonds just like NH3. When molecules are larger and they're still polar, the larger ones contain more dipoles. So I want you to imagine there's just more positives and more negatives. That means there's more forces of attraction. If you have more forces of attraction, then you have things that look more solid versus liquid or gaseous, because solids are any kind of matter that have particles that are extremely close together because of their attraction. That's why urea, which is larger, is going to be more solid than ammonia, which typically is a gas since it's just smaller. And they have different ways of explaining that here. You could have said urea has a greater molar mass. It has more electron density. It does. If it's larger, it definitely has more dispersion forces. There's more hydrogen bonding. It's more polar, meaning it has more dipoles. This is the one that made most sense to me. In 3G, sketch 2 different hydrogen bonding interactions between ammonia and water. Here is the answer on the mark scheme, but I want to draw it for you as well. So it says 2 different bonding interactions from hydrogen between ammonia and water. So I'm going to draw my ammonia here. And can you tell what's positive and negative? This is going to be the negative end, and all of the hydrogens are going to be positive since they are lower in electronegativity. And now I'm going to put my water. I'm going to put, let's see, one water here. And H is positive and O is more negative. And I can show this interaction site like this, for instance. I can make little lines like this, or I could have just done like an arrow or a line. All I'm trying to say is the positive of this H is attracted to the negative of this O. And over here, I'm going to do the opposite. I'm going to have the N be attracted to one of the H's on water. These are 2 different hydrogen bonding interactions. Since both of these molecules contain hydrogen bonds, I can hydrogen bond them to each other. All right, the combustion of urea produces water and carbon dioxide. That's usually what combustion produces for us. But they also pointed out that this particular one will produce nitrogen. What is always part of your combustion reaction? Oxygen is always the reactant. If you do not have oxygen, you cannot have fire. combustion, explosion, fire. You need oxygen, always. So this is just a matter of you putting together the correct reactants and products and then balancing it correctly. In number 4, I don't have too much to say other than pay attention to the marks. Here they're asking you why these molecules, which are all hydrides, meaning hydrogen is bonded to all of the elements in group 16, why they are polar, and it says 2 marks. So you don't just want to say there's an asymmetry. Asymmetrical would be accepted as an answer, but it's only going to give you 1 mark. You still want to say something like, well, each of the bonds in the molecule are polar. The reason is they're just different, right? There's different electronegativities between H and O and H and S, HSE. So there's a difference in electronegativities between the H's and everything that they're bonded to in each of these respective molecules. And then on top of it, there's an asymmetry, which leads to an uneven distribution of charge, or you can say dipoles that do not cancel out. You can explain that it ends up being bent, meaning there's lone pairs on it, and these lone pairs do not cancel out with the bonded hydrogens. Just make sure you're looking at marks and able to provide answers for that. 4B, I figure is easy for you. This is obvious, it's not what they're asking you, but H2O is up here because it's made of hydrogen bonds. Therefore, it has the highest of the boiling points. But these slowly increase because this one is heavier than this one's heavier than this one. The heavier you are, the more dispersion forces you have. So number of your electrons increases the heavier you are, and dispersion forces, meaning that now you have more forces to break. The NH2 ion, NH2 minus, I'm sorry, NH2 minus could have been drawn like this. 1, 2, 3, 4, 5. I'm going to add another electron here. 6. And then you would do and add this hydrogen here. Right? I wouldn't want to add the added electron to a hydrogen because then the hydrogen's complete and it wouldn't need to bond and it would just become an ion. So that's why you end up tetrahedral in the electron domain geometry, but bent or V-shaped in the molecular geometry because of the lone pairs that are here. Here, I feel like you guys are pretty good. In order to explain the general increasing trend in first ionization across a period, you definitely have to refer to the radius. The radius of every atom gets smaller because it gets 1 more proton successively, and thus every element increases in its effective nuclear charge, which is going to make it more difficult to remove electrons. So that means the atoms over on the right side of the periodic table will require more ionization energy to release their electrons. Same thing for 5B, 2 marks. Make sure that you're noticing you're talking about metals now. So you're going to want to consider that down a group as the metals get larger in their radius. What happens is there becomes more of a shielding effect, or there's more of a distance between the valence electron that they release in their metallic bonding and the nucleus. Wow, that one looks terrible, just terrible. So here they'll say the atomic or ionic radius of these metals increases down a group. However, there is a decrease in the force of attraction between the metal ions and their delocalized electrons. So if this here is lithium, which usually has 2 levels, it's actually now Li plus because it released its valence electron out, right? Wow, that's okay. We'll go here. It released its valence electron out. This one released it, this one released it, this one released it. So between this valence electron and this nucleus, there's less distance. than here to here, or here to here, or here to here. In all melting point questions, you need to consider bonding. Bonding is going to matter a lot. If they're talking about metals, then you need to reference the delocalized sea of electrons model in reference to the nucleus of the cations of the metals that are cations. If we're talking about nonmetals, then you want to consider intermolecular forces. Here for 5C, these equations, this one is for P4O10, another one is for sodium oxide, magnesium oxide. These are actually part of your book. So we went over them in topic 3, and I just want to make sure that you really make flashcards or something already, because they ask about these all the time, meaning I'm definitely going to be asking about them as well. In topic 3, we discussed acidic and basic oxides across period 3. And we said that the first two, which are the alkali and alkaline earth metals, when they bond to oxygen, they make alkaline substances, meaning basic substances. Aluminum is amphoteric, silicon all the way to chlorine, acidic. And then when each of these reacts with water, they produce something different. These things produce basic hydroxides, and we can see those down here. So these are two formulas you need to know by memory. This year and next year, they're both very important. P4O10, P4O6, SO3, and all the chlorines here, they always make acidic things, and you'll see that on the next page. The ones that they tend to ask about the most are these. So this is the one they're asking you about here in this question. They ask about these two and these two all the time. Just so that you know, silicates, silicon oxide, this one, when it reacts with water, doesn't make something acidic. It is the only acidic oxide that does not make an acidic product. It makes something called silicates. So everything else is going to make a product that matches its behavior, except silicone. So that is why that is the answer here. You have to just memorize that and get used to this, okay? This is bringing back topic 2. Remember that an emission spectrum is in reference to the data we receive when we look at the emission, the atomic emission spectra of an element. So this would, for instance, be a data sheet that I receive from a spectroscope, and then I get something like this. These lines are landing on different numbers. So maybe something here like 200 nm, nanometers for the wavelength, because we're talking about light now. So wavelength matters, whereas here it's going to say something like 50 nanometers, because these wavelengths are shorter since their frequencies are higher. And how do I know the frequencies are higher? Because the lines are super close together, and higher frequencies always have overlapping or at least close to converging energy levels. So if something is shooting out from that level, it's also going to shoot out at a close proximity. So all I have to say is an emission spectrum for hydrogen is a series of lines, or I can say lines that represent the frequencies or the wavelengths or the types of light emitted by hydrogen. The higher frequency ones converge, and that's what I'm showing here. (6A), I'm pretty sure you're fine. Let me know if you're not. 6B also. But notice that 6B says, predict with a reason whether the molecule is polar or nonpolar. You might still comment that its bonds are polar, but then comment Additionally, the bonds that are polar have dipoles that do not cancel out. Therefore, that is why it is polar, or you can just say it's polar because it's unsymmetrical in its charge distribution. There's a lone pair at the top, something like that, and that's fine. Number 7 has a exception that we just have to memorize, and that exception is here for 7C, I believe. No, not 7C. 7F. So, not 7F either. Oops. 7G, sorry. So titanium chloride. This looks to me ionic because it's a metal and a non-metal. But what I want you to always do from now on is look at table 8. Table 8 here in your data booklet contains the electronegativity values of every element here at the bottom. And so if we look for titanium and we look for chlorine, so chlorine is 3.2. That is not Ti, that is TL. Titanium is 1.5. So titanium 1.5, chlorine 3.2. That difference is not actually different enough for this to be ionic. So that is why this is mostly covalent. This is mostly covalent. Therefore, the melting point is actually lower than that of KCl, and you'll notice that the answer says titanium chloride is molecular. What I've done, honestly, is just memorize that TiCl4 is molecular and not ionic, and it's just helped me. They tend to only ask about this. They don't really ask about other exceptions, just this one. In 7E, there is a slide in the beginning of the topic 4 slides where I explain why alloys might have superior properties. So in pure aluminum, you just have aluminum atoms. And so you have a bunch of atoms that look the same because actually they become aluminum ions in order to bond, right? So here, let's say we have aluminum. It used to have 3 energy levels, but it released its 3 electrons. And so now what I have is Al3+ and Al3+. In an alloy, here's aluminum titanium, I'm going to have atoms that have different radii. So this actually makes it harder for things to just shift past each other, and that makes something like this alloy more difficult to bend or break. It's actually harder. This one might be more malleable because of all the shifting that can occur. This one is not as malleable. All right, number 8, I felt you guys should be okay with. Here you did have to remember topic 3. This would be an acidic product. This would be a basic product. This is covalent because it's got nonmetals only. This is ionic, and it's not one of our exceptions. It's a metal nonmetal. Ionic things, when molten, can conduct electricity. Covalent things, doesn't matter whether they're molten or not, they are not conducting electricity. And that is it for your assignment. So please let me know if there's something you need help with. A lot of you have emailed me, and that is awesome. Continue to do so. And just make sure that from here on out, you're still continuing to turn things in on time. I will be looking at timestamps, and I cannot give you credit if you did not turn it in on time. I hope this was, at least partially enjoyable, but mostly helpful. And stay safe, guys, and you'll be hearing from me again in the next lecture.